caution, curvy road ahead. We're looking for transition points, but keep in mind that even if a function behaves a certain way due to the geometry of the tangent lines, that does not guarantee that the function really is transitioning. In other words, we're looking for what are called critical values of the function, or values where the function is doing something strange, something critical. But critical does not mean the function's transitioning necessarily. Here are two examples. That is, look at the function here. I've drawn, well, two functions in red. On this first slide, we can see the function definitely is increasing from point A to point B, right? F of x is going up due to our definitions of functions increasing. But similarly, the function keeps increasing from B to C. So you'd say f of x is also increasing. In other words, f is increasing over its entire domain from point A to point C, right? You can clearly see that from the graph. However, look at what happens at B. At B, I can draw the tangent line, and look, the tangent line is flat. So even though we have a flat tangent line, it does not guarantee the function is transitioning from going up to going down, okay? So in this case, this was sort of a false positive. We see that the derivative of this function is definitely 0 at B. F prime at x is 0. Okay, and I could say f prime of x is 0 at x equal b. However, it's not a transition point. It is a critical point, right? Something critical happens in the behavior of the function, but it's not a transition point. After all, we're looking for transition points. Those are important points. Here's another example, okay? Clearly, the function is decreasing over its entire domain, right? As we increase in x, the corresponding y values are going down. No question. We can see it. But look, well, maybe I should write that first. So f of x is decreasing here, but it continues to decrease. But look at what happens at E, right? If I look at the tangent line at E, hey, look, I've got a vertical tangent line there. Vertical tangent line means the derivative does not exist at that point. But even if the derivative doesn't exist, it still does not indicate that there is a transition point going on here. It does, however, indicate that something critical happens in the behavior of the function. So clearly it's a critical value of the function, but it's not a transition point. Okay? So I can write that over here, that the derivative of the function does not exist, or more precisely, I can say the derivative of f of x does not exist, dne, at the point x is equal to e, at a particular point in its domain. Both of these functions are continuous functions and defined everywhere on their domain. However, even though something critical happens at certain values of the domain, they have no transition points, right? This function's always increasing, and this function's always decreasing. So the key here is that even though we've seen that the geometry of the tangent line has something to do with where the function might be increasing and decreasing, or in particular where it's transitioning, it does not guarantee that because we found a critical value of the function, that the function actually transitions at that value. So that's the caution here. We can look for critical values of the function. That's a starting place to look for transition points, but we still have to check. We have to do more checks to determine whether the function really is transitioning at those critical values. Let's take a moment to summarize what we've come up with so far. We were looking for where a function is increasing and where it's decreasing. In particular, even if we didn't have the picture in front of us, and if the domain goes on forever, we still want to know the intervals of increase and the intervals of decrease. And we saw that we could use the power of calculus and the geometry of tangent lines to help us achieve this goal. In particular, we were looking for transition points. If we can find where the function is transitioning from going up to going down, or from going down to going back up, we've figured it out, okay? And we're looking again for a systematic way of doing this. So we saw that in fact, one way to do this is to look for where the tangent line is flat, which is of course where the derivative is 0, or where the derivative does not exist. Those are two possible places where the function could be transitioning. Well, notice I've got a picture of a function drawn here. Clearly this function, without any doubt, is increasing between point A and point B, right? The function's going up as we increase in x. But at this one point, at point B, it transitions from going up to going back down. We see that, in fact, the tangent line is 0 at that point. That means the derivative is 0 there. We also see the functions clearly decreasing from point B to point C. And then again, it's increasing after point C from C to D. At point C, we can clearly see that the derivative does not exist there because we get some kind of weird vertical tangent thing. There's a corner point there. Okay, so these are two places where, in fact, the function may be transitioning. But we also saw some examples of where the function might be doing something else. Okay, in other words, it's possible that we have a critical behavior of the function. In other words, the function's derivative might be equal to 0, or the derivative might not exist, but yet the function is still increasing as it goes along. In other words, it's not transitioning. So we saw that, in fact, we could get a false positive. That is, our little test needs to be tweaked a little bit more. Okay? In particular, the transition points are among what are called the critical values of the function. Critical values are values in the domain where the derivative is either 0 or it doesn't exist. Okay? So here's my definition. That is an interior point, C. Okay? C is a point of the domain F at which the derivative is 0. It's 0 at that point C, or the derivative does not exist at that point C. It's called the critical point of F. It's a point that's in the domain of F. But again, a critical point does not guarantee that it's a transition point. What we're looking for, of course, is transition points. So the question is, what do we do once we determine a bunch of critical values? What do we do to determine whether or not the function really is increasing or decreasing? Or that is it really transitioning at that point? It turns out that we have to do a little bit more work once we've determined all of the critical values of the function, right? Places where the function is doing something critical. We still need to do one more test to determine whether the function truly is transitioning at that point.